This is the lecture for BMFG 1213 Engineering Materials, and we will continue on Chapter 12C, Functional Properties of Material, Optical Properties of Materials. This chapter will cover ClO2, analyze the properties of engineering materials based on its structure, which is included in Bloom's taxonomy analysis. At the end of this topic, you should be able to describe electronic polarization that results from electromagnetic radiation atomic interactions and able to explain why materials are opaque or transparent to visible light. Optical properties of materials. Optical properties. The response of materials towards the electromagnetic radiation, such as visible light, is always known as optical properties. Electromagnetic radiation, considered to be wave-like, consists of electric and magnetic components perpendicular to each other and to the direction of propagation. For example, light, heat, radio wave, and X-rays. The electromagnetic radiation have a specific range of wavelength. If we look at this figure, we can see that the electric wave are perpendicular to the magnetic wave in here, and combination of electric and magnetic wave will result in the electromagnetic radiation and will propagate at certain direction with the specific wavelength. The electromagnetic radiation can be divided into groups, depends on the wavelength. If you can see in here, for example, radio or TV wave, we start from 0.1 meter up to or exceeding 1 kilometer of wavelength. So we have in here radio TV, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays, where the gamma rays have the smallest wavelength, around 10 to the power negative 12 up to 10 to the power of negative 14. And also at the visible light, the light is propagate into 7 colors. Also depends on the wavelength. All electromagnetic radiation travels a vacuum at the same velocity. The velocity c is related to the electric permittivity of vacuum and the magnetic permeability of a vacuum through this formula. The velocity of electromagnetic radiation c are the function of frequency v and the wavelength lambda according to this formula, c equal to lambda v. It is more convenient to view electromagnetic radiation from a quantum mechanical perspective. Radiation, rather than consisting of wave, is composed of groups or packets of energy which are called photons. The energy E of a photon is said to be quantized by the relation H equal to Hv or Hc over lambda, where H is the Planck constant and E photon is proportional with frequency v but inverse with lambda. Light interactions with solids. When light proceeds from one medium into another, for example from air into solid substance, some is transmitted, absorbed, and reflect. The radiation intensity of the beam incident I naught to the surface of the solid medium must equal to the sum of the intensities of the transmitted, absorbed, and reflected beam, denoted as IT, IA, and IR, respectively. So we have in here I naught equal to IT, IA, IR in the unit of watt per meter square. So Chi is transmitted, A absorbed, and R reflected. Or we can have alternate form when divided by I naught, where T plus A plus R equal to 1. So we just divide all this formula with the I naught. So we can have this kind of formula T plus A plus R equal to 1. T is for transmit, A absorb, R reflect of the fraction of incident light that are transmitted, absorbed, and reflected by a material. So if we can see in this figure, we have in here incident light I naught. If the light proceed from air medium into another or into a solid, some light will be transmitted, certain light will be absorbed, and certain light will be reflected in here. So combination of transmit, absorb, and reflect equal to 1. Light interactions with solid. There are three types of interaction when the light uh, interact with solids. The first one is transparent, second one is translucent, the third one is opaque. For transparent, the light is allowed to pass through with relatively low absorption and reflection. So absorption will be low, reflection is low. For translucent, only a few or a small portion of light is transmitted. So with high degree of absorption and also reflection. While for opaque, the transmission of light is not allowed. So the light either will be fully absorbed or will be fully reflect or combination of absorption and reflection. For bulk metals opaque throughout the entire visible spectrum, which means all light radiation is either absorbed or reflected. Electrically insulating materials made to be transparent, while semiconducting materials, some are transparent and some are opaque. Atomic and electronic interactions. When the electromagnetic radiation hit the solid materials, there are two optical phenomena will occur due to interaction between the radiation and the atoms, ions, and or electrons. The two most important interactions are, the first one is electronic polarization. A rapidly fluctuating electric field is one of the components of electromagnetic radiation. For the visible range of frequencies, this electric field interacts with the electron cloud surrounding each atom to induce electronic polarization and to shift the electron cloud relative to the nucleus of atom. Two consequences of this polarization are: first, some of the radiation energy may be absorbed, and some light waves are retarded in velocity as they pass through the medium. The, the first one is radiation energy may be absorbed. The second one will be the velocity of the light wave are retarded as they pass through the medium. The second atomic and electronic interactions is electron transitions. The absorption and emission of electronic radiation may involve electron transitions from one energy state to another. Only photons of frequencies corresponding to the possible data is for the atom can be absorbed. by electron transitions. Stimulated electron cannot remain in an excited state indefinitely. After a short time, it falls or decays back into its ground state or unexcited level with a re-emission of electromagnetic radiation. As what we can see in this figure, there is an incident photon or electromagnetic radiation hit the solid and it will excite the electron from E2 up to E4. So, but this phenomena will only occur if the incident photon have the energy higher than the delta E. For example, this is the delta E for this process from E2 up to E4. So delta E will be E4 minus E2. So for this electromagnetic radiation to excite this electron, it must have the energy Hv must be equal or higher than the delta E of the atom. And that after a short time, the electron will decay back into its original state or the ground state, which also re-emit the electromagnetic radiation. So we move to the next subtopic, which is the optical properties of metals. Metals are opaque since incident radiation with frequency within visible range excites electrons into unoccupied energy states above Fermi level. All frequencies of visible light are absorbed by metals because continuously available empty states. Metals are opaque to all electromagnetic radiation except to high frequency radiation such as the X and gamma rays. Most of the absorbed radiation is re-emitted as reflected light, where the perceived color is determined by the wavelength distribution that is re-emitted or reflected. So, the metals are opaque because there is no transmission of electromagnetic radiation can pass through the metals, so there is no transmission is occurred because all of the photon from the electromagnetic radiation has been absorbed by the excitation of the electron from the valence bands to the conduction band. So the electron from the valence band will excite to the conduction band continuously. The excitation process keeps on going continuously because in metal the conduction band and valence band are overlapped. So the Hv will always be larger than the EF. So in the other words, the each or every photon from the electromagnetic radiation will totally absorbed by the continuous excitation of electron from the valence band into conduction band. In times, the excited electrons from the conduction band will decay back into their original condition or into the ground states, where this process will emit the secondary electromagnetic radiation. The emission also contains uh, contain colors depends on the wavelength. So the the electromagnetic radiation instead of transmitted will be fully absorbed and then re-emitted into the secondary electromagnetic radiation for metals. Optical properties of non-metals. There are three optical phenomena that occur in non-metals. The first one is refraction, is coming from the transmission, then reflection, and also absorption. The first optical properties of nonmetals is refraction. Light that is transmitted into the interior of transparent materials experiences a decrease in velocity, and as a result, it will bend. The phenomenon is called refraction, or the band transmitted light is known as refraction. This is the result from the fact that the light is slower in the material compared in the vacuum. So we have in here index of refraction n equal to speed of light in a vacuum over speed of light in a material C over B. By adding large or heavy ions such as plumbum can decrease the speed of light, where the light hence can be bent. We can see in here the lead glass have the highest index of refraction due to heavy ions due to the heavy ions of lead. And the intensity of transmitted light decrease with distance travel. The thicker the pieces, they will be less transparent. This is the other value of refractive index for some transparent materials. You can have in here a few type of ceramics and also polymers. The second property is reflection. When light radiation passes from one medium into another having a different index of refraction, some of the light is scattered at the interface between the two media even if both are transparent. The reflectivity R represents the fraction of the incident light that is reflected at the surface. By this formula, R equal to IR over I naught, where IR is the intensity of the reflected beam, while I naught is the intensity of the incident beam. If the light is normal or perpendicular to the surface, then R will be N2 minus N1, N2 over N2 plus N1 square, where this one, if the light is normal, so the light is normal perpendicular to the surface, then we can use this kind of formula. If the light is transmitted from a vacuum or air on the solid, so we can use this kind of formula, ns minus 1 over ns plus 1, where ns is the refraction index of that particular solid. The third optical property of nonmetals is absorption. The absorption mechanism of light involves valence band, conduction band, electron transition, which depend on the electron energy band structure of the metal. It's similar to the absorption by the metal, but for non-metal, there is energy band gap in here, so the applied electromagnetic radiation must have the energy larger than Eg to excite the electron up to the conduction band. So the energy will be absorbed by the photon and the electron will be excited to the conduction band if the energy from electromagnetic radiation is larger than the band gap. The maximum band gap energy for which absorption of visible light is possible is given as this equation, where Eg, or maximum band gap, equal to Hc over lambda, where lambda, by calculation, we can find the minimum wavelength for visible light to excite the electron. Selected absorption of nonmetals. Transparent materials appear colored as a consequence of specific wavelength range of light that are selectively absorbed. For example, blue light having energy of 3.1 electron volt, while the red light have the energy of 1.7 electron volt. If the E gap is below 1.8, so all the color will be absorbed by the material or full absorption. So the color will be black. For example, silicon and gallium arsenide. If the E gap in here is large, E gap is larger than 3.1 electron volt, so no absorption. So it will be colorless because the highest color in the visible light is blue light having 3.1. If the E gap is above 3.1 electron volt, so no absorption, it will be colorless. If the E gap in between partial absorption material has a color. Color of non-metals transparent materials appear colored as a consequence of specific wavelength range of light that are selectively absorbed. The color perceived is a result of the combination of wavelengths that are transmitted. For example, cadmium sulfide has band gap about 2.4 electron volts. Hence, it will absorb the protons having energies greater than 2.4 electron volt, which correspond to the blue and violet portion. But some of this energy is re-radiated as light having other wavelength, because maybe the combination of blue and violet. Non-absorbed visible light consists of photons having energies between 1.8 and 2.4 electron volt. Cadmium sulfide takes on yellow-orange color because of the composition of the transmitted beam. Non-absorbed plus re-radiated beam. Transmission. The phenomena of absorption, reflection, and transmission can be applied to the passage of light through a transparent solid. The transmitted intensity at the back face, IT, for incident beam of intensity I0 on the front surface of specimen with thickness L, and absorption coefficient beta is equal to this formula, or can be found by using this formula. IT equal to I0 multiplied by 1 minus R square exponent negative BL. Or we have in here incident beam, and some of the beam may be reflected, some of the beam may be absorbed, and only some of the beam will be transmitted. The transmitted beam can be calculated by using this formula. IT equal to I0 multiplied by 1 minus R square exponent negative beta L, where B is absorption coefficient, X is distance travel. Depends on the distance where you want to take. If you want to take at this distance, you just need to use this dimension, which is X. So remember this, IT over I0 equal to exponent negative BX. Opacity and translucency in insulators. So the light transmitted of 3 aluminum oxide specimen in this figure. The first one is single crystal material sapphire, which is have transparent property. Second one is polycrystalline and fully dense non-porous material, have a translucent. And the third one is polycrystalline material that contains approximately 5% of porosity, it will become opaque. A transmitted light beam is deflected in direction and appears diffuse as a result of multiple scattering events. Opacity results when the scattering is so extensive that virtually none of the incident beam is transmitted undeflected to the back surface. So the light cannot pass through this kind of material. We call it the opaque material. Optical properties. If semiconductor or insulator does not have many impurity levels in the band gap, photons with energies smaller than the band gap energy cannot be absorbed. There are no quantum states with energies in the band gap. This explains why many insulators or wide band gap semiconductors are transparent to visible light, whereas narrow band semiconductors such as silicon, gallium arsenide are not. Or in the other word, if we can see in this figure, for insulator, the band gap is much higher. So the EG will be higher than the HV of electromagnetic. But for semiconductors such as intrinsic semiconductor, the EG is much narrower, which is EG uh, slower than HV. So this one it will absorb this one, no absorption, no absorb. So in this kind of semiconductor or insulator, the light will not be absorbed by the material, so the light will transmit through the material. That's why it explains many insulators or wide band gap semiconductors are transparent, so the light will be transmitted. While for narrow band gap semiconductors, the light will be absorbed, so it will not become transparent compared to these wide band gap semiconductors or insulators. Some application of this kind of optical properties for emission: light emitting diode LED and laser diode LD. Absorption for filtering, for example sunglasses, they use silicon filters, so they will absorb, uh, they will transmit only infrared light with simultaneous blocking the visible light. We are using the silicon filters. If there are many impurity levels, the photons with energy smaller than the band gap energy can be absorbed by exciting electrons or holes from these energy levels into the conduction or valence band respectively. For example, colored diamond. As we know, the pure or the plain diamond don't have any color, but there are some kind of pink or blue diamond exist. Uh, this kind of diamond, the blue or pink diamond, get the colors from the impurity. As the impurity in the diamond uh, has lowered the or reduced the energy band gap to be lower than the HV of that particular color. We take the blue diamond where the impurity may lower the energy band gap of diamond lower than the HV of the blue blue color blue color, so the diamond will become blue. So this is one of the application by introducing impurity to change the physical properties of material. Application of optical phenomena luminescence. Some materials are capable of absorbing energy and then re-emitting visible light in a phenomenon called luminescence, such as fluorescence lamp. We have in here incident radiation or electromagnetic radiation. We hit the the material and it will excite the electron from the valence band into the conduction band. But the electron at the certain time will decay back or fall back to their original state or original level. When this occurs, it will emit the secondary electromagnetic radiation, which or the emitted light. The visible light is emitted when it falls back to a lower energy state at around Hb larger than 1.8 or lower than 3.1 electron volt. So this will, the emitted light, we call it as the luminescence. Fluorescence and phosphorescence, where we use the UV radiation to have various uh, various type of light in here. For example, by using the UV radiation uh, and heat the coating consists of beta alumina doped with tungsten europium, we can have this kind of light. We call it the phosphorescence. Photoconductivity. Charge carriers, for example, electrons, holes, or both, created in the corresponding bands by absorbed light can also participate in current flow, and those should increase the current for a given applied voltage. For example, conductivity increase. This effect is called photoconductivity. And this is the example if we apply the electromagnetic radiation to that particular semiconductor, the 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 photon will be absorbed by the material, and the electron will be excited into the conduction band, and the electron will the conductivity will increase the conductivity, while it will also create a hole in here, so it will help also in conducting the electric. Band gap of intrinsic photoconductors should be smaller than the energy of the photons that are absorbed. So the energy band for this kind of semiconductors should be lower than the Hv of the light. So the absorption can be occurred in this semiconductor. So this is the example of photoconductivity application, the night vision, solar cell radiation detectors, photoelectric cell, xerography, or CCD for digital cameras. And again, this is the mechanism of photoconductivity. If we have in here the incident radiation or the electromagnetic radiation uh, hit the semiconductor, and it will absorb the semiconductor will absorb the photon, and the electron will excited into the conduction band, so electron will conduct the electricity. For example, the photo detector by using cadmium sulfide. So we have come to the summary of chapter 12c, optical properties of materials. The first one, when the light or radiation shines on the material, it may be reflected, absorbed, or transmit. Then the optical of the material can be classified into the transparent, translucent, and opaque, where the metals are classified in the as a opaque material. So it will only causes absorption and reflection and no transmission. For non-metals, it may have full absorption when the energy band gap is below 1.8 electron volt, no absorption if the energy band gap is above 3.1 electron volt, or partial absorption if the energy band gap is in between 1.8 and 3.1 electron volt. Color is determined by light wavelength that are transmitted and re-emitted from electron transitions. And for refraction, the speed of transmitted light varies among materials. I think that's all for this topic. Thank you for your time. Thank you.